And if you put a north and a south together, they attract. Now, the Pauli exclusion principle that we have is something that's based on all the quantum numbers. What it says is that no two electrons can have the same quantum number in an atom. So they have to have an energy level. We say 1, 2, 3, 4, 5. They have to have a different, they can have the same L value, they can have the same ML value, but all four of the numbers, the combination of the four numbers has to be unique for every single electron. And what that shows us right here is that this is not correct. The reason why this would not be correct is this is a 2s2. So the energy level would be 2. The angular quantum number, because it's an s orbital, would be 0. The magnetic quantum number would be 0 because there are no subshells. And then the spin, as shown here, is both plus 1/2. That right there is a violation of the Pauli exclusion principle. So because two electrons in the same atom have the same principal quantum numbers. Now there is a reason for this. It is not just because somebody said so. The reason why is when you have these two electrons that are spinning in the same direction, that means that they are both north magnets. And two north magnets have a slight repulsion. Electrons themselves like to repel. So because of that, an atom will never be stable if the electrons are in the same state. But if you were to replace this one with a minus 1/2, that's now a south magnet. Even though the two electrons want to repel each other because they're both negatively charged, there is an attraction between the two because they have different magnets. And so because of that, that's enough to overcome the repulsion and allow them to exist in the same orbital. So there's a reason behind the Pauli exclusion principle that you should be familiar with. Next, we have the quantum number in the periodic table. We've already talked about this. 1s1, 2s2. It gets to be fairly easy where I can say, what's the quantum number of this one? Or what's the highest quantum number of this one? And you should be able to say, oh, it's in the 5th orbital, it's p, and then it is this. You should be able to do that fairly easily. Off-ball principles and degenerate energy levels. So, electrons are filled from the lowest possible energy state. So if a particular atom has 7 electrons, okay, it wants to take the lowest possible state. So it will take and put 2 electrons here. Okay, notice how I drew one up and one down because you can't have them both going up. Okay, then it puts 2 here. And then it gets to the point where there are 3 electrons left and there are 3 spaces. Okay, some people will do this and that would be incorrect. Some people will do this and that would be okay. Some people will do this and that would be okay. These are arrows. They're usually drawn as little half arrows. But the whole point of this is that the electrons will fill the lowest energy state first. You would never see an atom in which the electrons go here and here, and then here, 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 and they don't fill up the lowest energy level. Okay, they will always fill up the lowest energy level because remember, electrons are negative. The nucleus is positive. So they want to come as close to each other as possible. It's the lowest possible energy state. Oh, and this right here is a little diagram that tells you what the energy states are going to be. So you just write the S column, the P column, the D column, the F column, and then you come diagonal. So 1s would go first, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. So notice how 3d is even after 4s. So this is how you would figure out the energy levels between the two. Another thing that you should notice is, as far as the energy differences between the two, if you notice there's quite a wide gap between 1 and 2, but as you go to 3 and 4 and 5 and 6, the energy differences get much, much smaller. The Zeeman effect is the experimental evidence that we had in order to figure out what the magnetic quantum numbers were, the fact that there are orbitals. What they did is if you take a spectrum line, okay, so in other words, they have sodium, and sodium produces this spectrum line. They take that same sodium, that same canister of gas, and they apply an external magnetic field to it. That's what this north and south is. It's a magnet. Well, when they apply a magnet to it, it splits up into 3 separate lines. And so the question is what's going on there? Well, the answer is there are three different orbitals. You have this one, and you have this one. One of these things is lining up, one of these orbitals is lining up with the magnetic field, making it more likely that it's an energetic line. So it shifts this line over just a little bit. The other one directly opposes the magnetic field. Okay, and I'm just picking them at random. This one opposes the magnetic field, and so it actually changes its energy to here. This one is perpendicular to the magnetic field, so it has no effect at all and just stays where it is. So the Zeeman effect was actually the experimental evidence that we had these suborbitals. And you see that here. Not all electrons of the same orbital are equal electrons. There must be suborbitals. Now, just so you know, if there is no external magnetic field, the energy level of all the p electrons are the same. Okay. Now, if you put it in a magnetic field, now there are very, 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 very small differences. I mean, these are extremely small differences in energy. And it does not determine which one is X, which one is Y, and which one is Z, because if I change where my magnet is, you'll have three different energy levels. Hunds Rule. Hunds Rule is the idea that like charges repel, and so the electrons want to be as far away from each other as possible. Because of Hunds Rule, you will fill one electron in the px, one in the py, and one in the pz before adding a second electron in each orbital. Now notice that doesn't apply to the 2s orbital. Okay, so what happens in the 2s orbital is you fill it first, and then whenever the suborbitals have the same amount of energy, you fill them one at a time. But the difference is on the energy diagram, you have 2s's here and 2p is here. So see how these are on the same level and this one is below it. So you would fill S and then you would fill P. Now this is particularly important when we talk about carbon. Carbon is oftentimes drawn like this. That's the Lewis dot structure of carbon that most people are familiar with. But if you were to do it in actuality, one of these represents the S and then the other three the P. Well, if you were to follow the energy level diagram, it would look something like this. So actually the correct annotation for carbon would be 2 in the s orbital and then 1 in each of the p orbitals. Now, carbon can easily obtain energy to kick one of these electrons up to here. That's why carbon has the ability to form 4 bonds, is because it can easily jump this gap. But in actuality, carbon should be 2 and then 1. Representing atoms. You should be familiar with the idea of electron configuration from first year chemistry. You should be able to take this right here and say it's hydrogen, or it's the electron structure of hydrogen, or taking this and tell me it's fluorine. This right here represents the energy level. This is the number of electrons in each orbital. So as an example, you can also do shortcuts. Shortcuts are going to make a lot of sense, especially whenever you have very, very large atoms. So you see this is the electron structure of potassium, but this right here represents a noble gas. You can only do it for noble gases. You can't do things like, oh, silver plus, you can't do that. But if you have a noble gas, that represents a complete orbital or valence structure. So in other words, the electrons are full up to that point. So then you can just say, okay, it's just like argon plus 1 extra electron. Okay, but once again, you can only do that with the noble gases like helium, neon, argon, xenon, krypton, those sorts of things. So here's an example. You have an atom with 34 protons. Okay, 34 protons tells me exactly what the element is going to be, and you should be able to tell me that the element is from your periodic table. You see right here that it's going to be maybe a different electron structure based on the fact that we have multiple electrons. So if you were to count the number of electrons, we have 2, 4, 10, 12, 18, 28, 30, 36. So we have 36 electrons. Whenever you have a difference in the number of protons and the number of electrons, you know you have to write it as an ion. The fact that there are 2 more electrons than there are protons tells me that it is going to be 2 minus. Okay? So you'd have to take a look at your periodic table, and you have to say, okay, what's the element that has 34 protons? You would write it right there. you'd have the charge of 2 minus. Say, what is the element that is predicted by the electron structure? And then it says, note, it is kind of tricky. Okay, so this is an interesting one because of this right here. The first thing that you want to do is you want to write it in a standard notation. So if you write it in a standard notation, it'll be much easier for you in terms of trying to figure out exactly what it is. So the first thing we can do is we can say, where is the last time that I have a complete orbital structure? And that would be right here, this 5p6. Okay, if you were to take a look at the 5p6 on your periodic table, it would be much easier for you to identify exactly which element we're talking about here. Well, if you were to do that, let's pull up our periodic table real quick. You could say it is, I think it's xenon, right? I don't have my periodic table with me. I think it's xenon, but check that. Then the last thing you have is you have this 4f1, 5d1, 6s2. So what that means is you have to add one element from the d orbital, which is there. Then you have to add one from the f orbital and the 2 from the 6s2 orbital. So at this point, it looks like this element would be not thorium, but selenium. It's a tough one. It says not everything follows the rule. So you have AR4S1 3D10 rather than the expected AR4S2 3D9. You are not expected to know exceptions to the rule. Okay, there are exceptions, just realize that there are. So if I give you a question that says this is the electron structure, it's an exception to the rule, just be prepared for that. Okay, you don't have to know them, just kind of think about why it may happen. Okay, electron configuration in the periodic table. There are similarities in chemical properties because of the similarity in valence structure. So if you look at the halogens, they all have this structure right here. 2p5, 3p5, 4p5, and so they have similar reactivity because of that. Okay, so alkali metals always end in an S1, and they're highly reactive because they want to get rid of one electron. Alkaline earth metals always end in S2, and they are generally reactive but less reactive than alkali metals. Okay, the chalcogens, which are sometimes just called group 16, always end in S2p4. Okay, they're generally reactive and they generally like to take electrons. The halogens are always S2p5, so it could be 4s2, 4p5, and that's a halogen. And they're very reactive and they really want to take electrons. And then finally, you also have the halogens, the noble gases, and the noble gases always end in S2p6.